All right, let's review our flowchart again. So our first step is, do we have a recognizable form, either geometric or p-series? If we don't have that, then we're going to try the divergence test. And we'll take the limit as n goes to infinity. If that limit is not 0, then it diverges. But if it does, then we look to see, do we have positive terms or alternating terms? So we covered a couple tests for positive terms. So now we're going to look at our alternating terms. And we're going to start with our alternating series test. Before we get to that test, I want to talk about probably one of the most famous alternating series called the alternating harmonic series. So we already know that the harmonic series is that 1 over n, so it's 1 plus a half plus a third plus a fourth plus a fifth, that we know diverges. The alternating harmonic series, the terms are going to switch signs. So it'll be 1 minus a half plus a third minus a fourth, and so on. Okay, and I'm going to show you how we get that out of this formula here in just a second. Okay, if you're ever stuck with an alternating series and you're really just not sure what's going on, it's always a good idea to just write out a few terms so you can get a sense of what's going on with your series. So let's go ahead and do that. We're going to use this graph below to plot out the first 10 terms of the sequence and then the first 10 partial sums as well. So I'll get you started on that, and then I'll have you pause the video and give it a try on your own. Okay, so when n is equal to 1, I have negative 1/2 to the 0, so that's a positive 1 over 1. So this is going to be just equal to 1. When n is 2, I have negative 1 to the first power, so I get a negative 1 over 2. When n is 3, I get a negative 1 to the 3 minus 1, so negative 1 squared over 3, so it gives me a positive 1/3. When n is 4, I get negative 1 to the third, so I get a negative 1 on top and a 4 down below. Okay, so let's take a look at what this is going to look like if we graph it. I'm going to graph these with this turquoise color and an X. So each one of these lines here should represent about 1/10 or 0.1. At least that was my plan when I made this. So when n is 1, my first term of my sequence is equal to 1. When n is 2, my second term is negative 1/2. So there's that one. When n is 3, I get a positive 1/3. So somewhere around there. When n is 4, I get a negative 1/4, so about negative 0.25. Okay, so here we have these starting to go like this. I'll let you fill in the rest of those. And then let's look at what those partial sums would be. So my first partial sum is going to be a 1, because I'm just adding up the first term. My second partial sum, I'm going to add up the first 2 terms of the sequence. So I get 1 plus a negative 1/2. So I get a positive 1/2 or 0.5. Okay, my third partial sum, now I'm going to add 1/3 to that. So I get 0.83. My fourth partial sum, now I'm going to subtract 1/4 from that. So I get 0.583. Okay, and I'm going to let you go ahead and pause the video and find the rest of those once I mark them on here. So let me get that started for you. So 1, 2, 3, 4. There's this one. There's that one. And here's the fourth one. So here's my partial sums. They look like they're going to kind of oscillate up here a little bit. But I want you to go ahead and give that a try. Pay careful attention to those partial sums because I'm planning on giving you an exam question where I ask you to calculate a partial sum. Not a huge one, but you do want to feel comfortable doing this process. So give this a pause and fill in the first 10 of each, the first 10 terms of the sequence and the first 10 partial sums. All right, so I had Excel go ahead and calculate these for me, and then so I have a list of values, and then I created a table with a plot. So these blue dots represent the sequence, and as you might suspect, that sequence is converging on 0. These orange dots represent the partial sums. Okay, and they're clearly converging here too. It looks like somewhere, I don't know, maybe around 0.7 or so. So it turns out that Euler proved that this alternating harmonic series is going to converge to the natural log of 2, which is a really interesting proof if you want to look that up sometime, but this is going to the natural log of 2. All right, so when we come back, we'll take a look at the requirements for the alternating series test.